Sometimes the mark scheme, even when you've seen it, doesn't help. And for the trickier questions in this homework, I've had a go at talking through how I would do them without peeking at the mark scheme first. So we've been told the mass is 580 kilograms. That's our M value, and that's in the standard unit. I haven't got to do anything to that. We're told the car gains 39,000 joules of gravitational potential energy as it goes from P to Q. So we're going to get a point first for recalling the equation that we have to not just be able to apply but learn and apply. So we are being asked for the change of gravitational potential energy is equal to the mass times the gravitational field strength times by the change of height, our MGH equation. And that's really quite kind of the question, to separate the marks out like that and lead us into which equation we're going to need to use. So calculating the height, so we've got to rearrange the equation, but let's substitute in first with the numbers that we know. So we know the gravitational potential energy, we know the mass, and we are being reminded that we are taking gravity, as we always do, as a 10 newtons per kilogram, and it's the change of height we're trying to find. So if I solve that step and get it down to 3 parts, I can then, if I want to, use the triangle method, and I can say if I put my finger over 1, 2, 3 zeros, then I would have 5,800 and the change of height down here, which would mean that if I put my finger over the thing I'm trying to find, it's showing me I need to do the 39,000 divided by the 5,800, which I am going to do on a calculator. I don't do that one in my head. And the answer that I get is, I'm going to round it neatly to 6.7, and that is a height that I've measured, so that would be in metres. 6.7 metres would be my final answer. I hope that tallies with the mark scheme. Probably should have looked at that before I recorded the video. So we're being asked what's happening to this roller coaster between R and between S. So the roller coaster is going to hit the water. The water is going to push back on that roller coaster car. There is going to be a huge amount of friction between the car and the water. That friction, that rubbing between the water and the roller coaster car, is going to transfer energy from the kinetic energy store of the car to the kinetic energy store of the water and the surroundings of the water. So there's going to be lots of energy transferred because of friction, or work done against friction. And the energy is going to go from being a kinetic store in the car to a thermal store in the water and in the surroundings. So we could get our keyword in here. It's going to be dissipated to the surroundings. So my final answer would be, between R and S, there will be lots of energy transferred because of the frictional forces. The energy that was stored in the moving car, the kinetic energy, will be transferred to thermal energy in the water, which will end up dissipated to the surroundings. 2 marks? We've been told right at the start of the question, though, that this student has a mass of 60 kilograms. We are also told about their downward force, their weight as well in newtons, but we won't need that for this question. You'll notice there was one part of this question that I cut out because we're not quite ready for it yet. So in part C, we're being asked to calculate the change of gravitational potential energy, and this time we're not being prompted to remember the equation. We've got to remember the equation though. So we start with that the change in gravitational potential energy is the mass times the gravitational field strength times the change in height. We're being also given a mark here for the unit, so before I do anything else, I am going to get that mark by being on the right page, I hope. that mark would be joules. I don't know why it won't let me write on there. But anyway, the unit would be joules. I'm going to get 1 mark before I've even done any maths. Let's substitute in what we know. What do we know? Well, we know the height from the question here. We know the height is 50 metres, so we can substitute in the 50. We know that gravity is always worth 10 on Earth. We know the mass is 60, and so we don't need to rearrange for this equation, and that is kind of a clue in the mark there. For 3 marks, you wouldn't expect to have to know a unit and rearrange for 3 marks. So we're getting a mark for recalling the equation, we're getting a mark for the unit, and we're getting 1 mark for this working out for the timesing together of 60, which I am going to do on a calculator. 60 times 10 is 600 times by 50 gives us a total of 30,000, and that is joules. So I've worked that bit out. Hopefully that's the same answer as we have managed to get with the mark scheme. I really should check those mark schemes. What's happening at the point when the bungee jumper has maximum kinetic energy? Well, that will be at the very bottom of the fall. After they've fallen that 50 metres, all of their gravitational potential energy has at the bottom all become kinetic energy. So they'll have got faster and faster and faster. They'll accelerate through the fall. And when they reach the bottom, that 50 metres, that's the point when they're moving the fastest. And that's when they will ping back up. But at that point, it may even be the forces have balanced before the bungee jumper has reached the whole 50 metres. It might have got to a point where the force is balanced and actually they were moving at a terminal velocity, at a constant speed at the end. But the maximum kinetic energy they could ever have would definitely be at the bottom of that fall. That was a lot of explanation for 1 mark, sorry. Finally, the maximum kinetic energy in real life is likely to be less. So stating at which point, at that point it would have this 30,000 joules of kinetic energy. But in real life, why that would be less is because of dissipation. Dissipation of thermal energy to the surroundings. Some of the energy is going to be transferred through air resistance, and that frictional force is going to change some of the kinetic energy store into a thermal energy store of the surroundings. And we get to use the key word dissipated again there, don't we? This question is actually getting your head round what it's telling you and what it's asking you to do. So we're being told that these students are doing an investigation. So they're looking at what it's like with meteorites impacting the Earth. And they're using balls instead of meteorites. And they're using a big tray of sand instead of the Earth. So they've got a tray of sand. My amazing drawing happening here. And they've got a ball. Okay. Now, they're going to use 6 different balls with different masses. That's what it's telling us. So their variable that they're changing is how much mass is dropping into the sand. Well, I've got 1, 2, 3, 4. I've made that a bit big, haven't I? 5. And they started with a really little one. Look. So they've got 6 different masses, but they are dropping all of these balls from the same height. So say, for example, they fix their height here to 1 metre. I'm going to say 1 metre because that keeps numbers really easy for us when we're thinking about equations. When we've not been given numbers, we can make numbers up to help us think about them. But we always make those numbers nice and easy. So this first bit of the question is asking us about the gravitational potential energy and the mass and the relationship between the two of them. So we have to go, well, we know something about gravitational potential energy. You can calculate it from m times g times h. And in this experiment, g is fixed. We're doing all of these experiments in a classroom somewhere on Earth. So we know that that's fixed at 10 newtons per kilogram. And the students have decided to fix the height. And if they were sensible, they also would fix a height that gives you a nice easy number. 1 metre is ideal. That means that the gravitational potential energy is equal to 10 times 1, 10 lots of the mass. So as we change the mass, as we make the mass bigger, the gravitational potential energy is going to get bigger. More massive objects raised to the same height will store more GPE. But there's actually then a choice between A and B on these graphs, so that's wiped these two out. But A and B are still possible. They're both showing that as the mass increases, the gravitational potential energy increases. But the key thing here, I mean, if you imagine this was 1, 2, 3, 4, 5 and 6 kilograms for our masses, we could actually get our head round it by saying, right, well, okay, in the first experiment, 10 times 1, when you've got 1 kilogram, you're going to have 10 joules. When you've got 2 kilograms, 2 times 10, you're going to have 20 joules. When you've got 3 kilograms, you're going to have 30 joules. Joules. And so on. So 440. I'm not going to keep going. I think you've got the idea. Every time the mass goes up by 1, the energy is going up by 10. Therefore, they're proportional to each other. As the mass increases, the gravitational potential energy increases. But they are doing that in step with each other, which means we get the straight line graph. That's why the right answer is A. Okay, not because I guessed it, because I thought it through. And that was a long explanation for 1 mark, but a lot of revision in there too. So, how will the energy of the ball change as it's dropped? And that's what we've been learning about that's led to this homework, isn't it? We're starting with a gravitational potential energy store, and the ball is falling towards the sand. That gravitational potential energy is being transferred into kinetic energy, into the kinetic energy store of the ball. And as the ball falls, the gravitational potential energy store goes down and the kinetic energy store goes up, because there is a law of conservation of energy that says the total amount of energy has to stay the same. And so all of the gravitational potential energy at the start with the stationary ball becomes all of the kinetic energy just as that ball hits the sand. And yeah, you could argue there's going to be some air resistance, and therefore there's going to be a tiny little bit of energy that's wasted to the surroundings, dissipated as thermal energy, but that's not relevant in this answer. It's going to be such a small amount of energy. For 2 marks, I would be focusing on gravitational potential energy changing into kinetic energy, and the idea that that total amount of energy has to stay the same. So for example, saying as the gravitational potential energy becomes less, the kinetic energy becomes more. As one decreases, the other increases to keep the total amount the same. That's what I'd be doing for my 2 marks. However, the dissipated bit is important here, because that last 2 marks, we're being asked about the work done. And we've talked about work done being exactly the same as the energy transferred, which is what the textbook is sort of quoting here. And we do more work on work done in year 11. But we've done enough to be able to answer this question, because we can change that word in there. Explain how work is done. Explain how energy is transferred when the balls impact the sand. So what happens? We've got a ball with a full store of kinetic energy, as it were, and that moving ball is going to stop when it hits the sand. So this store of kinetic energy that's in the ball has got to go somewhere. So the ball has kinetic energy, and then the ball doesn't have any kinetic energy, but it can't just disappear. However, as the ball collides with the sand, there's going to be a huge amount of friction. There's going to be a lot of force between the sand and the ball, and that sand is going to be pushed out of the way. The sand is going to move. So the kinetic energy from the ball is going to be transferred to actually kinetic energy of the sand, as well as some of the energy being dissipated to the surroundings. It's going to warm the sand up and warm the surroundings up. And that, I hope, will get us the marks on that question. I'm going to go and check the mark schemes now.